In section 9.4, we talk about comparison of series. The limit comparison test is a test that works for positive series. Like the direct comparison test, the limit comparison test will compare a complicated series with a simpler series. This test works very well with fractions who has n's raised to a power in both the numerator and the denominator. To create the simpler series, or the comparison series, use only the terms with the highest degree in the numerator and the denominator, but do not use the coefficients. The limit comparison test says, given two positive infinite series, a sub n and b sub n, if the limit of a sub n divided by b sub n is equal to some positive number L, then a sub n and b sub n will both converge or diverge. In other words, they will both follow whatever b sub n, your comparison series, does. If your comparison series converges and you get a positive number L, then both a sub n and b sub n will both converge. If b sub n diverges and you get a positive number L, then a sub n and b sub n will both diverge. For this example, we want to know if the series 3n plus 2 over n squared plus 4n minus 1 from n equal 1 to infinity converges or diverges. This is a series that will work well with the limit comparison test because we have n's raised to a power in the numerator and in the denominator. The first thing we need to do is establish what our comparison series b sub n looks like. To find this, we're going to compare the variable with the highest power in the numerator and divide it by the variable with the highest power in the denominator. Do not use the coefficients. We're going to simplify this so that we get 1 over n from 1 equal 1 to infinity. We know that this is a p-series where p equals 1 means the series diverges. So our b sub n diverges. Now we're going to evaluate the limit of a sub n, which is our original series, divided by the b sub n, which is our comparison series, as n approaches infinity, to see what we get. So remember, that gives us the limit of a sub n is our original. That was 3n plus 2 divided by n squared plus 4n minus 1. And then we're going to divide this by the b sub n. Remember, we said that b sub n was equal to 1 over n. And now we're going to simplify this. This means, and by the way, this is a complex fraction. It means we're going to take the limit as n approaches infinity, and we're going to take that top fraction, 3n plus 2, divided by the n squared plus 4n minus 1, and multiply it by the reciprocal of the denominator, so n over 1. Now we're going to simplify this. This gives us the limit of 3n squared plus 2n divided by n squared plus 4n minus 1. Now let's apply the limit. So now when we substitute the n's for infinities, we have 3 times infinity squared plus 2 times infinity. This gives us infinity in the numerator. In the denominator, we have infinity squared plus 4 times infinity minus 1. That gives us infinity in the denominator. What we found is the indeterminate form. when you have the indeterminate form, that says that you can now use L'Hopital's rule in order to evaluate this limit. However, remember, if you have n's in the numerator and denominator, there's another way to evaluate this. One way to evaluate this indeterminate form is to take the limit as n approaches infinity on the leading terms, which is 3n squared divided by n squared, and simplify this. This means that we will take the limit as n approaches infinity on 3. The limit of 3 is equal to 3. We could have used L'Hopital's rule to also evaluate this limit. And remember, for L'Hopital's rule, we would take the derivative of the numerator, which is 6n plus 2, and take the derivative of the denominator, which is 2n plus 4, and then evaluate. So 6 times infinity plus 2 is infinity. 2 times infinity plus 4 in the denominator is infinity. And you have the indeterminate form again, so you would have to do L'Hopital's rule again. That would mean we have the limit as n approaches infinity. The derivative of the top, the derivative of 6n plus 2 is 6. The derivative of 2n plus 4 is 2. This gives us the limit as n approaches infinity on 3. And again, this is equal to 3. So as you can see, we're getting the same answer both times. It's just two different ways to do it. They're both fine, whichever way you work it. Since the limit is a positive finite number, the original series will follow the convergence or divergence of the comparison series. Since b sub n, which we said was 1 over n, diverges, that means that a sub n, 3n plus 2 over n squared plus 4n minus 1, will also diverge. For this next example, we're going to determine whether the cube root of n over n squared plus 1 converges, diverges. Again, this is a good opportunity to use the limit comparison test because there's n's with the power in the numerator. And when I say n's with the power, meaning this cube root of n is equal to n to the 1/3 power, and there's n's with a power in the denominator. First thing we need to do is create a comparison series. So that's going to be our b sub n. And the way we find b sub n is we're going to take the variable with the highest power in the numerator. That would be n to the 1/3, and divide it by the variable with the highest power in the denominator, which is n squared, from n equal 1 to infinity. Now we need to simplify this. So this is going to be the sum, and since 2 is larger than 1/3, I'm going to move the 1/3 to the denominator. That gives me 1 over n squared minus 1/3 from n equal 1 to infinity. Let's simplify this. N squared in terms of thirds is 6/3. So 6/3 minus 1/3 gives us 5/3 in the denominator. So here again, we have a p-series. Where p equals 5/3, which is greater than 1, converges. So now we know our b sub n converges. Let's go use the limit comparison test. We're going to evaluate the limit of a sub n divided by the b sub n as n approaches infinity to see what we get. Hopefully, this is going to be equal to some number L that's a positive number. So we're going to take the limit as n approaches infinity with the a sub n. A sub n is our original function. That would be n to the 1/3 power divided by n squared plus 1. And what we want to do is divide it by the b sub n. But because b sub n is also a fraction, instead of dividing by the fraction, we're going to multiply by the reciprocal, which is n to the 5/3 power divided by 1. And now we're going to simplify this. This gives us the limit n to the 1/3 times n to the 5/3 gives you n to the 6/3, or n squared. This is going to be divided by n squared plus 1 times 1, which is this n squared plus 1. Let's apply the limit. So infinity squared is infinity, and infinity squared plus 1 in the denominator is also infinity, and we have the indeterminate form. I'm going to simplify this by taking the limit as n approaches infinity on the leading terms, n squared divided by n squared, and simplifying this so that I will be taking the limit of 1 as n approaches infinity. The limit of 1 is equal to 1. Since the limit is equal to 1 and our b sub n converged, that means a sub n will also converge.